All right, section 3.4, we're looking at multiplication of whole numbers. Probably of all four of these sections about basic arithmetic, this is my favorite one. It's got the most interesting algorithms, I think is why. I think that there's some really cool stuff in here. So what I'd like for you to do is to do the same thing we did at the beginning of class last time. Do you remember what I had you do? Move. So move, get close to the person you're supposed to be working with group work, and you'll be there for the end when we actually go to group work anyway, because in about 1 page worth, we're going to be creating some word problems of our own, just like we did last time, okay? So shift to where your group partner is. Okay, so like we were doing in both of them, in addition and subtraction, the first thing we're going to do is we're going to define what do we mean by multiplication, okay? So multiplication. So for finite sets A and B, if the number of items in set A is little a and the number of items in set B is little b, and n is not 0, then what we mean by n times A is that this is A added together n times. And we've used this definition when we did Gauss's method. I don't know if you remember that, where we changed it to being addition of all the same stuff, and then we said, hey, we added this together 36 times. We could have just multiplied by 36, or whatever the numbers were. Obviously, that only works for n not 0. It has to be a whole number. A and B are counting numbers. This is all whole number stuff. There's similar descriptions for what addition, multiplication, all these things are when we're working with other numbers, but we're just defining them for whole numbers right now. So by definition, if we let n is equal to 0, we're going to say that 0 times A is 0. And then if we multiply A and B together, what we're actually going to get is we're going to get the number of items in the cross product, which is a throwback to chapter 1, 2, whatever it was. I think 2 is where we saw that, right? The number of items in A times the number of items in B is the same as the number of items in the cross product that we were doing before. The Cartesian product is I think is what Rubric calls it. Okay, all that look good? Okay, so we have, I think it's 3. Yep, 4. There's 4. We have 4 models for multiplication. And again, with these models for multiplication, the difference is in how the structure of the language is worded, okay? It's how the word problem is written as to which model might be the most reasonable way to think about it. So here's our first one. This is the repeated addition model, which kind of mimics our definition of multiplication most closely. Giselle takes 3 tests every Friday. After 4 Fridays, how many tests has she taken? So in some sense, we're taking a test, 3 tests this Friday, next Friday, the 3rd Friday, the 4th Friday. We're having 3 added together 4 times, okay? And just like our definition above, this means 3 times 4, and whether you've added the 3 together 4 times or whether you multiply it before, you get the same answer, which is 12. And so these are word problems, which means if there's context, in which there is, of course, we're going to write the context of the value that we found. So this is 12 tests. So we call it units sometimes, right? Write the units on the answer. There's 12 tests. Okay, does that make sense? Okay, model number 2, again, different phrasing or different descripting of the problem. Menu is baking cookies. He is able to place the dough 3 cookies wide and 6 cookies long on his pan. Right? It doesn't say Menu is making cookies. He makes 3 cookies today, 3 cookies tomorrow. That's not what's happening. Right? We've got a picture of what's happening here that's different than the last one. How many cookies will his pan hold? So it says he's got 3 cookies wide and 6 cookies long. And so we're going to draw a picture of Menu's cookies. They're not going to be a very exciting picture, but that's okay. We're going to draw them anyway. So ours is just going to be circles. It says that it's 3 cookies wide. I should have done it the other way, just a second. We'll do it long like this since I have more space. So there's 3 in one direction, and it's supposed to be 6 in the other direction. Okay. 3 cookies wide, 6 cookies long. We can add them together, or we can recognize the multiplication effect that's happening here. How many cookies do we have? There's 18 cookies. This is an array, is what this is called. Now, this model, array, is very similar to the next model called an area model. The difference is, much like the difference between our set models and our measurement models for addition. When we did set models, they were objects we were counting. This is objects to be counted, right? We're counting cookies, okay? When we did the measurement model, it was space to be counted. So the space was actually something that could be subdivided, and it would make sense to talk about it that way. So when we're looking at the next one, that's what we see. It's an area model. An area model means I'm counting space. How much space something is. Alexis is planning a garden. She has a space that's 5 feet wide and 7 feet long. How much area does she have in which to plant? Now, if we changed it slightly, we could turn this into an array question. It could say she's planting 5 plants wide and 7 plants long, right? And I'd be counting plants, but I'm not actually counting plants. I'm counting space. That's what makes this an area model. So for my picture, I do draw a rectangle. Our rectangle can be written, if you would like, with these dimensions in. So this is 5 wide and 7 long. And we can even subdivide the picture to sort of see the imagery, especially when we're first explaining or describing it to our students. And so we can create, 5 sort of lengths in here. They should all be approximately equal. You can make it sort of believable. And then the 7 wide. That was pretty good spacing on my part this time. It was nice. So this is a 5 and this is a 7. We can actually count the number of little gridded boxes. And in doing so, we will end up with 5 times 7, which is 35. Because we are talking about area, we do need to be careful of our units, right? This was 7 feet and 5 feet. And what happens when I multiply feet and feet? You get square feet, and we write it like feet with a square on it. Yeah, we read it as square feet, but feet with a square on it. Okay, so you want to make sure your units match. Okay, is that all right? All right, our last one mimics pairings best. So our last one is the Cartesian product, which is what we mentioned in our description it's like the description we did down here, right? This is the Cartesian product. So it's mimicking this part of the definition that we'd seen before. And it has to do with pairing things up, choosing objects. Unique is at a pizza place. She can choose from 2 types of crusts, thin or original, and 3 types of toppings, pepperoni, sausage, ham. How many different types of pizzas could Unique choose? So we can put them in pairs. I'll draw a couple of imageries of this so you can see. We could put them in pairs like we did the Cartesian product. I think I have some space over here. I do. Where we say that she picks, I'll do capital T for thin and I'll do O for original in a minute. Okay, so a thin crust with pepperoni. She does a thin crust with sausage, or she does a thin crust with ham. Or you could say she does original crust with pepperoni, original crust with sausage, original crust with ham. And we would see that we have 2 times 3 or 6 types of pizza. So this is one visual imagery that we could go with for this to work. Okay, that mimics what we've described as a Cartesian product, maybe the best in terms of a visual. There is another way to do this, and for those of you who've had proportional and statistical reasoning, you'll recognize it. If you haven't, it's okay too. But another way of doing this is to sort of mark this like you would in a tree diagram. So the first choice you're going to make, think about actually making the pizza. The first choice you really have to make is what kind of crust it's going to be made with. That's the first choice. So you can do thin or you can do original. And then the second choice, and again, these are all 3 options off of the pizza crust option, is that we can have pepperoni, sausage, or ham. Pepperoni, sausage, and ham, like such. And again, we get 2 times 3 or 6 types. Those are 2 sort of visually different ways of thinking about our description, but both work equally well, just a different option. Okay, so Your job now is to create 4 word problems like we did last time when we did our 3 word problems, 1 for each of these types. Make sure as you're discussing it that it really fits in with the type that you're describing. Is it really a repeated addition or is it really more of an array, right? That kind of a thing. Okay, so discuss it and create 1 word problem for each category. Make sure that you're willing to at least read 1 of those, if not 2 potentially, out loud when we get back together, okay? Okay, let's take a look at what you guys had. So each of you had the job of writing down something. So somebody tell me what you have for repeated addition.
We have math class 3 times a week, and then after 3 weeks, how many math classes have we had?
Okay, math 3 times a week. After 3 weeks, how many have you had? So one nuance to this that you might sort of think about is maybe not making the numbers the same in case that's a confusion factor for kids and you're trying to identify what issues are causing problems. So that's something to sort of keep in mind. Next, somebody else want to do this one? Okay, let's do another one. How about array? Who wants to do array? Yes.
Mackenzie is setting up her classroom. She's able to place 4 desks long and 5 desks wide. How many desks will the classroom hold?
Excellent. Desks in a classroom is a really good array kind of imagery. Yeah, for sure. Okay, very good. Anybody else have an array one that you're particularly fond of? Man, y'all aren't fond of much today, are you? How about area? Who wants to do an area one? Yeah, Abby.
We said President Thomas wants to add 25 feet by 35 feet to the back of Rayleigh Chapel. How much area is he going to add?
Okay, very good. Adding space to an existing structure. Cool. What'd you have, Ethan?
Greg is building a house that is 37 feet long and 28 feet wide. What is the area of floor tiles that he needs?
Okay, yeah, definitely tile is something that works really nicely for this imagery too. Okay, how about Cartesian product? That leaves both of you guys. You guys both get to talk about Cartesian products. What do you have?
Okay, we put James getting ready for school. She has to choose between 3 shirts and 4 pairs of pants. How many possible outfits can she create?
Outfits. I think that's what you guys did too, is outfits, didn't you? Yeah. Outfits works really nicely for a Cartesian product example. Did you guys do something with ice cream? Is that what I was hearing?
Yeah.
Go ahead and read what you have.
I think we're trying to figure out how to word the question, phrase it, like at the end.
Okay.
End.
Maybe we can help you. Go ahead and read what you have so far,
Okay.
Faith.
Betty is getting ice cream from her friends. There are 3 ice cream flavors: vanilla, chocolate, and strawberry, and 2 topping choices: caramel and sprinkles.
Okay.
Like, how many?
How many sundaes can she create? We could go with that one. Yeah. So, or you could say how many one topping, sundaes could she create, something like that. Yeah. So very clearly say she only gets to pick one. Yeah. Very good. Okay. So does that help? So I wanted to take just a second to sort of talk about like why in the world are we doing this to some degree. So number one, we want to have reason for motivating the need for multiplication. And these are legitimate reasons to multiply, so that's good. But also, it's important to be aware that not all questions have the same structure. So if you're working with a kid and you start noticing a pattern that every single time that it's something that looks like area, they're not getting it, that gives you a lot more information on how to help them. The issue may not be that they don't know how to concrete just multiply 3 times 4. It might be that they can't take the word problem and turn it into language in a math way. And I have a child in my house that has difficulty with word problems in math. She can memorize fantastically. She's really good at math from a computational sense, but from a application sense, she has a learning disability. And so this was something that they were able to identify when they did her IEP, actually. So just as an FYI, that's why we're doing this, is to have us have that kind of experience. Okay, we're going to look now at properties for multiplication. We actually have 6 properties for multiplication. We only had 4 for addition. So we have the closure property, and the closure property is much the same as the closure property with addition. It just says that if you have 2 numbers and you multiply them, whole numbers, you get another whole number. All right, whole number times whole number is whole number. You can't do whole number times whole number and end up getting, a negative, or whole number times a whole number and end up getting a fraction. Right? That doesn't happen. Whole number times whole number, it is a whole number. Commutative property says that you can multiply in any order. This is a wonderful feature. This is why memorization of like your multiplication tables works so nicely as you add, like the 3s and then the 4s and then 5s. It's because you're adding fewer of the multiplication facts on as you go. I don't need to know what 7 times 4 is because I already learned what 4 times 7 was, right? I already know that. And I just need to be able to reverse it and recognize it's the same thing. So the commutative property. Associative property says that the order in which we multiply, like in a list of numbers, doesn't matter. So if I multiply A times B and then times C, it's the same as multiplying the B and the C first and then times the A. And again, why is it helpful? Well, sometimes two numbers multiplied together are much more convenient, especially if they multiply together, you get something that's got a 10 in it, or a 0 at the end. The two numbers multiply give you 30 and it ends in 0. Wonderful. Ending in 0 means I don't really have to do as much to get the next multiplication piece. So multiplying things out of order is sort of allowed. Identity property. So again, jot this in like we did on addition. This is the multiplicative. Hang on. Identity property. The multiplicative identity property specifically says there's this number 1, whereas our additive identity was the number 0. So 1 is the multiplicative identity. And the reason it's the multiplicative identity is because when you multiply by it, either A times 1 or 1 times A, you get back A. And we use this for lots of things. One of the things you use it for when we get to rational numbers, which is a proportional statistical reasoning section, is that you use it to create fractions that have like denominators, right? I can multiply by 7 over 7 and it doesn't change the value. And then I get a denominator that's like something else so I can add and subtract fractions. We use it there. So this multiplicative identity is really important. We also have the multiplication property by 0. It's not an identity, right? If you multiply by 0, it zeroes everything out. That's what it's saying. So is A times 0 and 0 times A are both 0. And then we have the distributive property. It's over addition or subtraction. So this combines addition or subtraction with multiplication. And it says that if I have A times either B plus C or B minus C, I can distribute the A across the parentheses, and it's AB, and then plus or minus AC. Okay, so take just like 2 minutes. We'll say 2 minutes. There's 6 problems, and you're supposed to identify which property is present. I'll flip it back in a second, Faith. Which property is present? Okay, if you're not quite done, it's okay. Let's fill them in so that we can go ahead and head to the group work in a second. What's the first property? Right, it's multiplication property of 0. How about the second one? That's commutative. Don't let parentheses throw you. Commutative property. What changed was the order within the parentheses. How about the second, C? That's associative. The actual numbers within the parentheses changed, right? Or you could say that the location of the parentheses changed. How about D? Yeah, it's the multiplicative identity. It says if we multiply by 1, it doesn't change. How about E? That's the distributive property. Okay? And F looks the weirdest, but do you know what property it is? It's distributive again. So what's actually happened is this grouping of 1 plus 2 has distributed through. That's just another number. So it is also the distributive property.